So I'm taking one example here. In this example, light moves in a medium that has its refractive index n. It's given by this relation. And refractive index is continuously changing with y. Suppose a light ray that enters into this medium almost grazingly, it's grazing incidence, almost making 90 degree with the normal. And suppose the medium here is air having refractive index almost equal to 1. So the light will go on a curved path. It will bend continuously because n is changing continuously. You can imagine many parallel boundaries like this, many parallel boundaries, and these boundaries are very close. They're continuous boundaries, and light is continuously refracting from one boundary to another boundary. So we have to find the trajectory of this light. So we have to find the equation of this trajectory. So for that, take a general point on this trajectory. That I'll do. So it's a general point, x comma y, you can say. It's a x comma y. This is an interface between two different media, because n is changing, and therefore I'm saying media is continuously changing. So this is a boundary between two different ends, the n just above it and the n just below it. There are different values, and so therefore the light is refracting here. So we know that when light suffers refraction through many parallel surfaces, the value of n sin theta everywhere is same. So the n sin theta at this value will be equal to n sin theta anywhere on this trajectory. So n sin theta here is 1 sin 90, and n sin theta here is general n sin theta, whatever theta here is. And this theta can be written in terms of theta dash, where theta dash is the angle which the tangent at this point makes with the horizontal. So sin theta is equal to cos theta dash, and therefore we have found cos theta dash equal to 1 by n. Now imagine a triangle like this, a 90-degree triangle. Cos theta dash 1 by n implies the base is 1, hypotenuse is n, and we have found this perpendicular using Pythagoras theorem. And now from this triangle we can find tan theta dash. This is root of n square minus 1. Now put the value of n which is given in the question, and putting that value of n and solving will give y plus 1. So, and what is tan theta dash? Tan theta dash is the slope here, and slope is dy by dx. So therefore we can write dy by dx equal to y plus 1. Now we have to bring all y values on one side and all x values on other side. We have to separate the variables, and then we have to integrate. Since the light is passing through origin, so x equal to 0 and y equal to 0, these are the values of one of the limits, and it's by passing through this a general point x comma y, so x and y are the other limits, and on solving we get this value. So this is the equation of path. Okay, in this example we have to find the relation among the unit vectors. So this is incident light, and there is a unit vector I cap along this direction. This is normal, unit vector along normal, and this is the direction in which refracted light goes. So a unit vector along this direction is r cap. Refractive indices are NA and NB, and we have to find the relation among these vectors. So for that, just apply Snell's law, NA sin theta equal to NB sin theta b here. Okay. Now check what I cross n is. I cap cross n is. So it is the value of I cap 1, the value of n cap 1, sine of angle between these two vectors. And what is the angle between I cap and n cap? So I cap is in this direction while n cap is in this direction. So the angle between them is this angle, which comes out pi minus theta a. So therefore, I cross n is 1 sine pi minus theta a. And if you use right hand rule, if you turn your right hand fingers from I vector to n vector, your thumb will point outwards, so its direction is outward. Similarly, if you apply r cross n, so the angle between r vector and n vector, this is pi minus theta b, and so it will come out sine theta b, and the direction of this is also outward. Now, so in this equation, put the values of sine theta a and sine theta b. First, you do what you do, put outward direction here and here. Put outward direction. Now, sine theta a in outward direction is equal to I cross n, so it will become na I cross n, and sine theta b in outward direction will be r cross n. So simply put r cross n. So this is a relation which we needed. Okay. In this figure, there is a slab, parallel slab, put in air. The thickness of slab is T. A light ray is passing like this. So we can easily see that light, when it comes from air to air, will become parallel to itself, but it will displace from the original direction of light. It will shift laterally. So instead of going straight, light is now going in this direction. So light has shifted by this much amount. So this displacement is called lateral displacement. So we have to find this lateral displacement, and that can be done easily. Just see this diagram. So this distance is t, and therefore this distance will be t sec r from this triangle. This angle is I, this angle is r. It's obvious notations. This is I minus r. So this distance is t, the thickness of slab. This is t sec r. Now come to this triangle. So in this triangle, you know t sec r, and you have to find lateral displacement. So from this triangle, it is t sec r sine of I minus r. So this is the formula for lateral displacement. Now refraction through flat surface. So there is a flat surface. An object is placed at this point O, and we have to see where its image will be formed. You can imagine that there is an observer here in this medium N2. So I have taken two light rays, one striking normally. It will not bend, it will go straight. Because if you use Snell's law here, I is equal to 0, so R will also be equal to 0. Now I have taken one more ray, and this ray will bend either way. So I have just shown in one direction. Now the observer here will feel that these rays are coming from this point. So the observer here will see this object here. So this point is image. Suppose object distance is d from the interface and image distance is d dash, and light is originally in N1 medium and then in N2 medium. It's going from N1 to N2. So the relation among all these quantities is found to be this: d dash is equal to d upon N1 by N2. Let's see the proof of it. So in this diagram, I have shown the object, these two rays. Suppose this angle is theta 1, suppose this angle is theta 1. So since these rays are parallel, both are normals, and third ray is cutting. So if this angle is theta 1, this will also be theta 1, alternate angles. And suppose this angle is theta 2, so this will also be theta 2. You can verify these two are again parallel rays, and this ray is a straight line. So these are corresponding angles. Now if you apply Snell's law at this point, This will be n1 sine theta 1 equal to n2 sine theta 2. Now, if all these angles, theta 1 and theta 2, are small angles, then we say that these rays are paraxial rays. So, paraxial rays are those which make small angle with the normals. So, if the angles are small, what we can do, we can replace sine by tan. Now, see the figure, tan theta 1 is from this figure, tan theta 1 is x over d, while tan theta 2 is x over d dash from this triangle. So, we have this relation. Okay. We do not have to use any sign convention for this formula because there is a rule that object and image, they always are in same medium. In case of flat refraction, the object and image always lie in same medium. So therefore, we do not have to use any sign convention to find the position of image. N1 is the medium in which light is present before refraction and N2 after refraction. Or you can say that light is moving from N1 to N2. Now, there is a parallel slab put in air. So, 1, this is refractive index of air, refractive index of air. This is refractive index of the slab, N, and an object O is placed here. A light ray is moving like this. It will bend. And suppose some observer is here in the glass. For that observer, light rays are coming like this, and one ray is coming like along this principal axis, along this normal, like this. So for an observer here, the rays seem to come from this point. So we'll say that after refraction through this surface, the image formed is here. So suppose this distance is d, this is d1 dash. So these distances will be related by this formula. d1 dash is d upon 1 by n. Why 1 by n? Because light is moving from 1 to n. So therefore, it is nd. So this distance is nd. Now light rays will strike the second surface. And these rays are striking on the second surface. These are incident rays on second surface. And the intersection point of incident rays. What is the intersection point? If you extend these rays backward, the intersection point is I1. So intersection point of incident rays is defined as object. So for this second surface, I1 becomes object. And suppose light ray after refraction moves like this. So for an observer here, the rays will seem to come from this point, I. So that will be the position of image. So for the second surface, if you apply the formula, again the same formula. So d2 dash is the distance of image, and d2 dash is this distance. This distance is d2 dash. Sorry, this distance. Now distances are from this surface, second surface. So d2 dash. So d2 dash is equal to object distance. This is object distance, d1 dash plus t. So object is I1 for this surface. And the object distance from this surface is t plus nd. So it is t plus nd. And now light is moving from n to 1. So divided by n oblique 1. So it is like this. So on solving, it becomes d plus t by n. So this distance d2 is d plus t by n. Now, if this point is n, this is O. So n to O distance is, you can see, it is t plus d. NO is t plus d. While n to I distance, and I distance is this d2 dash, which is d plus t by n. And the distance between O and I, this distance is called shift. So for an observer here, this object will be seen shifted from its position by this much of amount. So OI is the shift, and how do you find OI? By subtracting NO and NI from NO. So if you subtract, so it becomes d plus t minus d plus t by n, and it is t minus t by n. Okay. So that becomes a formula for the shift. So you can apply this formula to find shift, t minus t by n. If the shift comes out positive, suppose you apply this formula and the result obtained by putting the numerical values is positive. Positive shift implies in the direction of motion of light rays. So light rays are moving in this direction towards your right, and if the shift comes out positive, it means object is shifted rightwards and the image is seen there. And if this comes out negative, it will be the just opposite of that. So object will be shifted against the motion of light ray, that is away from the observer. So this is the formula, t minus t by n. Now I've taken again, there is an object, this medium is n1, n2, n3, n4, and light will move from object and it will refract 1, 2, 3 thrice and then finally come to n4 medium. So this is object, suppose t1 distance from this surface. So it's a flat surface refraction, so we can apply that formula, d1 dash. d1 dash is the image distance. Suppose this light ray is bending like this, this will go straight. So for an observer here, the observer who sees these light rays, that observer will see this object at this point, d1 dash distance from the interface. So d1 dash will be equal to that formula. So it is t1 object distance upon, now since the light is moving from n1 to n2, so divided by n2 upon n2, sorry, n1 upon n2, and that n2 goes in the numerator. So it is d1 dash as shown in figure. So I'm calling this as S1, S2 and S3 surfaces. Now for S2 surface, light rays are striking like this. So the intersection point of incident rays, these are incident rays for S2. So the intersection point of incident rays, that happens to be object. So this point is object. This point is object for S2. Okay. So I'm going to apply the formula, refraction formula for S2 surface. So it will become d2 dash. Suppose light is moving like this after refraction. So these light rays, they appear to come from, if you extend these rays, so these will appear to come from this point. So these rays form image here. So the distance is d2 dash. So d2 dash will be equal to t2 plus d1 dash. Okay, this is object distance and object is here. So its distance from S2 is d1 dash and t2. So it is t2 plus d1 dash, and now light is moving from n2 to n3. So it will be divided by n2 upon n3. So n3, that will come on the numerator side. So it will become like this. And if you put the value of d1 dash into this, it will be like this. So now light is in n3 medium. After passing through S2, it is now in n3 medium. And d2 dash, we have this formula. If you note, the light has passed T1 and T2 by now. And now the formula is T1 by N1 into N3 plus T2 by N2 into N3. If you separate this N3, forget about this N3. Light has passed T1 and T2, so we are having this term T1 by N1 plus T2 by N2, and since light is now in N3 medium, N3 is multiplied. So there is a pattern you can see. Now for S3, light rays are coming like this, and we know that incident rays, they come from, or they seem to come from object. So object will be this point for S3. This is object. And if the rays are moving like this, then the refracted rays that seem to come from this point, so this is image. Apply the formula. So d3 dash is this distance, d3 dash. This is equal to, now object distance. So object distance means this total distance. So that will be d2 dash plus t3. So t3 plus d2 dash, and light is now moving from n3 to n4. So n3 upon n4, so n4 will go on the upside. And just put the value of d2 dash, which you have found here at this point, and solve. So this relation is obtained. So again you say the same pattern is repeated. Now light has moved T1, T2 and T3, and now it is finally in N4 medium. So therefore we have T1 by N1 term, T2 by N2 term, T3 by N3 term, and all terms are multiplied by N4 because light is now in N4 medium. So you can apply this formula directly to find the position of image from the final interface. So this is final interface through which the light is passing. So the final position of image distance, and this distance is from final interface. This is first interface, second interface, third and final interface. So from final interface, the distance is this. So this distance is called apparent depth. This is called apparent depth. Apparent depth. So this is the depth of object as seen by an observer here, because the observer here is seeing the object at this point, So this is the object that, so this is the depth that is felt by the observer. Okay. So just taking an example to digest what we have just learned. So this is an object, this is 20 centimeter, 10 centimeter, 12, 14, and these are the refractive indices of all these media. And the question is, find the apparent depth. So we can find that, we can apply the formula directly. So first light is moving 20 centimeter. So 20, and it is n equal to 2. So 20 by 2 into 2. And what is this 2? This is the refractive index of this final medium. Plus, now light will go move this 10 distance. So 10 upon 1 into 2. This 2 is common. That is the refractive index of this final medium. And similarly go on adding and solve. It is 80 centimeters. So the observer will see this object 80 centimeter from this surface. So this is the apparent depth. Again, the same situation, an object, these are the T1, T2, T3, T4, T5 thicknesses, and this is observer, this is object. Now we have to find image to observer distance. So wherever image is seen, so that position and observer position, the distance between these two. Okay, so T1 by N1, this is T1 by N1 plus T2 by N2 plus T3 by N3 plus T4 by N4. We'll go on adding like that. And plus T5 by N5. This is T5 by N5. This is not a necessary thing. This is not a mandatory thing. You can write up to this point, T4 by N4. Writing up to this point, T4 by N4, will give depth from this surface. But now we are finding the image distance from observer. So we need to find distance from this point. Therefore, we are adding T5 also. And since light is finally in N5, so this whole will be multiplied by N5. Okay, so this is observer image distance. While to find shift, how much this object is seen shifted. To find that, suppose that this is object, this is image, so this is shift. So observer to object distance, this total distance minus observer to image will give the shift. So observer to object minus observer to image. And what is observer to object? It is summation of all these t values. So that I have written in short, summation of t, this is summation symbol, summation of t minus observer to image, which is written here. That is also written in shortcut notation. So all summation of all t by n values can be written as t by n, summation of t by n, and then finally multiplied by n5. So this will give summation of t bracket 1 minus 1 by n into n5. Just apply that formula in this case. This is observer, this is object, we have to find the shift. So shift is equal to summation of t bracket 1 minus 1 by n into 1. Why 1? Because light will be finally in air, so it will be 1. So T1, 1 minus 1 upon n, so n here is air, into this one is common, plus 15, this is 15, bracket 1 minus 1 by n, so n is 2, into 1, this one is common, plus T2, this is T2, 1 minus 1 by 1, air, so 1 by 1 into 1, plus 10 for this, 10, 1 minus 1 by 3, n is 3 here, into 1, and plus T3, 1 minus 1 by 1 into 1. So this is a shift. So what do you notice here? That certain terms are 0, and those terms are all those terms which are air terms. This is 0, this is 0, this is 0. See, the medium in which observer is present, it is air. So all those media which are similar to this medium, which is air, so all air medium will have no shifting. If this was all air, the object would be seen at the same position if it was all air. So shifting is produced only by those media which are different from air. So those media are these 15 centimeter and 10 centimeter width media. So while finding shift, we can altogether neglect those media which are same as the final medium. The final medium is air. So we can neglect this air, and this air. There is no shifting due to these airs. So we can write only these two terms. And solving, it comes out plus 14.1. So what this positive means? Positive means the object will be seen shifted towards the direction in which light is moving. So since light is moving from object to observer, so the shift will be in this direction by 14.1. So here image will be seen. Okay, thank you.